Dear students, we are going to see solution to few physics problems which were uploaded in mock CET. Let us start with this problem. A sphere of mass m moving with the velocity v collides head-on another sphere of same mass which is at rest. The ratio of final velocity of the second sphere to the initial velocity of the first sphere is. It's also given E is the coefficient of restitution and the collision is inelastic. So what you are asked to find? You are asked to find the ratio of the final velocity of the second sphere to the initial velocity of the first sphere. So let us start with the first sphere having a mass which is equal to m and is moving with the velocity v. This is now colliding with another one sphere which is having the same mass m, but it is having an initial velocity to be 0 because it is at rest now. Okay, these two collide with each other. So after collision, what would happen to the velocity of the first sphere? Let us take the velocity of the first sphere to be v1, and what would happen to the second sphere? That would be having a velocity which is equal to v2. And it is also given that the collision is inelastic. So the momentum before collision obviously would be equal to the momentum after collision. So we can write initially for the first sphere momentum to be m into v, and for the second sphere that would be m into 0, right? That is actually equal to the momentum after collision. So this is m into v1 plus m into v2. So this I can write it as mv, which is nothing but m into v1 plus v2. M and m we can remove it, so we can write v is nothing but v1 plus v2, right? And E is the coefficient of restitution. So we know the formula E, which is the coefficient of restitution, to be v2 minus v1 upon u2 minus u1, where v1 and v2 are the final velocities and u1 and u2 are the initial velocities. So this would become v2 minus v1 upon u2. It is nothing but v, and your initial velocity was 0, so we take that to be equal to 0, right? So this is nothing but E, it is v2 minus v1 upon v, right? So we can write this as EV, which is equal to v2 minus v1. But we are asked actually to find out the ratio of final velocity of the second sphere to the initial velocity of the first sphere. So we need to modify this in such a way that we take the ratio of the final velocity of the second sphere to the initial velocity of the first sphere. So what I am going to do, I am just going to add v on both the sides of this equation. Okay, so if I add v on both the sides of this equation, we know that v, it is nothing but v1 plus v2. So this v1 would get cancelled. I would get this to be equal to 2v2, which is nothing but ev plus vv. Or we can take v to be common, so this would become e plus 1, which is nothing but 2 into v2. So we want the ratio of the final velocity of the second sphere to the initial velocity of the first sphere. That is nothing but e plus 1 by 2. Hence the correct option is answer C, which is e plus 1 by 2. Okay. Now we would go to the very simple another one problem. The molar specific heat of an ideal gas at constant pressure and constant volume is Cp and Cv respectively. If R is the universal gas constant and the ratio of Cp to Cv is gamma, then Cv is equal to what? So this is very simple. We know the formula connecting Cp and Cv. So from kinetic theory of gases, we know that Cp minus Cv, it is nothing but R, which is the molar gas constant, right? And what is given? Cp to Cv, the ratio it is given as gamma, isn't it? So we can write this to be Cp, which is nothing but Cv into gamma. I am just going to substitute Cp to be Cv gamma. So the above equation now would become Cv gamma minus Cv, which is equal to R. So I take CV common, so this would become gamma minus 1, which is equal to R, or I can write CV, it is nothing but R upon gamma minus 1. Okay, so the correct option is answer D, which is CV is equal to R upon gamma minus 1. I hope this is very simple and easy. Thank you.